In fact, it's even more interesting than that. There was this lovely paper published last year in Science by some people at UCL, which was looking at what happened when you've got here a CA1 hippocampal neuron, which is essentially a coincidence detector. In other words, it gets a signal in one branch, it gets another signal in another branch, and if the two signals are close enough in time, then it fires, and if they're not close enough in time, then it doesn't fire. So what they were doing with a computer program called Neuron, they were putting a signal in here, they were putting a signal in there at a different time, and seeing the time at which it fired. And they were interested in how this was influenced by electric fields or something like that. And they showed this graph, which was what happens when you vary the time of the input by 5 milliseconds and what happens to the time of the output. And as you can see, as it gets closer and closer to the not firing, the effects of 5 millisecond delays get bigger and bigger. So I got interested in this, understandably, and they sent the computer model that they actually used for this. I'm going to take that one as read, actually. And you can run this you can run this same computer model. You can look at the actual time at which the signal needs to arrive in order to start in order to cause the neuron to fire. And you can vary it in the computer in exquisite sensitivity. So having found the exact time at which you need the edge, if you like, at which you will just not fire if it goes 1 microsecond or 1/10 of a microsecond further, you can then start going backwards and finding out how much the time of firing of the neuron depends on the time of the input. And what you find, sure enough, is that when the neuron is almost on the edge of not firing at all, a very small change in the time of the arrival of the second signal makes for a very big change in the time of the neuron firing. So the delay that we were talking about, due ultimately, say, to a single calcium atom arriving at a different time, can get amplified by a factor of 10 or even 100 or even, in extreme cases, 1,000. Now, you've got 10 to the 11 or so neurons in your brain. They're all firing connected in extremely complex ways, asynchronously. If there's the slightest chance of very small uncertainties in the timing of firing being amplified, then you're inevitably going to get to the point where the brain becomes wholly unpredictable. In the following sense, not wholly unpredictable in the sense that you've no idea what's going to happen next, obviously, but in the sense that you can never be absolutely certain what's going to happen. In other words, the brain is not some kind of robotic mechanism. It's much more subtle and interesting than that. It provides a way in which what we want to call the active information in your mind can influence your behavior, and you can suspect what people are going to do. You can predict in a probabilistic way. It's highly unlikely that I'm about to flap my wings and speak Russian, for example. But you can never be totally certain. So what I hope I've convinced you of is, first of all, that informational objects exist, that the world just isn't as simple as matter and mathematics. Secondly, that the brain is not just a deterministic machine, and that there's a plausible mechanism that goes from the known indeterminacy of very small level events, like positions of a calcium ion, to indeterminacy at the levels that will influence whether neurons fire or not. So neuroscience does not imply determinism. If the whole of the world is deterministic in some funny way, then of course the brain's deterministic, but so is everything else. But if there's real indeterminism in the position of calcium ions, then there's real indeterminism in how the brain behaves. And therefore, the language of minds and souls and free will, understood as talking about informational objects, is perfectly compatible with science.